Okay, so here's the example, another example that we'll do here, determining the rate equation, the rate law. The textbook says rate expression. So we're determining how the concentration of the reactants kind of affect the rate in a a mathematical or quantitative matter. So again, if you look back to the lesson, if you're wondering kind of where we're starting here, but for this example, remember what we want to do is we want to find out what factors affect the rate. So we know that there's going to be some constant, and we're going to try and find out if one or both of these reactants right here, okay, these are the reactants, I didn't write down the equation, sorry. These are the reactants for the equation. We're going to find out if one or both of them affect the rate. Okay, so there's our equation right there. So we want to examine the data. There's only 3 trials, so this shouldn't be too hard, right? If you look at trial 1 and 2, we see that the concentration of hydrogen peroxide is held constant. What we're changing is the concentration of hydrogen iodide, HI. So what's happening here? Times what? Times 2 to the power of 1. Let's always try and include some exponents there, just while we're determining this, okay? So what's happening to the rate then? This is happening. Now this might not be totally obvious, but what's happening here? Okay, yeah, it's doubling. And how do you know? Well, what you could do is you could, on your calculator, if you don't see that right away, how many times this is going into. You go 0.0152 divided by 0.0076, and you'll get 2. And so this is doubling as well. And it's 2, what? To the power of 1. So do you see how this number is exactly the same as this number? More importantly, base the same, exponent the same. So does the concentration of HI have an effect on the rate? Yes. To the power of what? 1. So in our rate expression, we're going to write, yes, the concentration of HI is definitely affecting our rate. And to the power of 1, you do not have to write to the power of 1, just write concentration of HI. Okay, everyone? Everyone good with that? Okay? Everyone good with that? So let's take a look at then hydrogen peroxide here. And let's see what's happening. Between trial 1 and 3, okay, those are the same. You see that? So hydrogen iodide is not changing, but hydrogen peroxide is changing, and it's doubling, right? Times 2 to the power of 1. What's happening? Again, we want to make sure we hit the right trials, 1 and 3. What's happening between trial 1 and 3 as far as the rate goes? Yeah, this one's pretty easy, isn't it? It's doubling as well. So we see that the rate is directly proportional to the change in HI and also the change in H2O2. To the power of what here? 1. Yeah. Okay, that's pretty easy, right? So here's our rate expression here, or our kind of incomplete rate equation. Rate law, rate expression, rate equation. The equation should have the value for K as well, so that's the complete equation. So that's what we're going to do next. We're going to solve for K, and again, just like we did in our previous lesson, let's pick one trial, doesn't matter which one. Let's plug in the values. I'm going to pick 3 this time. It's right here. And let's plug everything in. So this is 0.0152. Now we should check in our chart. Okay, yeah, it's not times 10 to the negative whatever, so it's just that's the actual number. So we put that number in there, and we're going to solve for K. What's the concentration of HI in this trial? 0.1, and the rate expression says we take that to the power of 1, so that's good. H2O2, here's the concentration of H2O2 in trial 3. That's 0.2. And that's also from our rate expression here. It's to the power of 1. So this is what we've got. Capiche? Solve for K by dividing by 0.002. Oops, 0.02. 0.1 times 0.2. And what do you get? K equals 0.76, and yeah, we have Yeah, sig figs, don't worry about sig figs so much. We just got one sig fig here, but 0.76 moles per liter per second. No, sorry. It is not that. That's the rate. Constants, typically you don't have to put a unit, but if we did put a unit here, the rate is going to be in moles per liter per second. These concentrations, see, this is the thing, the unit for the constant actually changes every time. So the units are not important. But this is molar, right? So the constant here is going to have to reconcile these units. So we've got moles per liter squared. We need to get to moles per liter per second. So what's the units going to be here? We won't write it, but what's it going to be? So let's just figure that out real quick. Moles per liter is going to be equal to what unit times moles squared, molar squared. What gets us that? Well, we need to get rid of the squared, so we're going to have molar there. And we need to have seconds on the bottom, so we need to have seconds down there. So the units here will be 1 over moles per liter times seconds. And again, it's going to change for every equation. So the constant, we're just going to say, don't worry about units, okay? I won't ding you on the test for this, no. Good question. You will not have to have units. Okay? Any questions so far about that example? All right. No units on the constant. Now, if we're completing this, all right, for the very final answer here, then your rate equation is going to be rate equals this number, 0.76, and then write the concentrations of those reactants that are involved in changing the rate. So that's your complete rate expression. Complete rate equation. Okay, any questions? Okay, so there's your example worked through with the trials and determining the exponents, and there's your final answer.